Welcome to the Mechanics of Solids lecture series. In this series of videos, we'll work some examples solving for shear and bending moment diagrams in beams. Specifically, we'll use a set of simple rules to plot the shear and bending moment diagrams directly without having to derive the shear and moment functions first. This will save some time. The first example that we'll look at is a simply supported beam with a concentrated moment at the end. I like to solve this example because it develops some intuition for how a concentrated moment is resisted in a simply supported beam. To save time, I've extended the lines down for the shear force diagram and bending moment diagram plots, and I saved some room in the margin to do calculations. We'll start off by solving for the reactions. I have a reaction A sub y at support A, and I have a reaction B sub y at support B. Taking the sum of the forces in y equal to 0, I have A sub y plus B sub y equals 0. There are no other loads acting in the y direction on the beam. This tells us that A sub y must be equal to negative B sub y, or the reactions must be equal and opposite. And indeed, to resist the concentrated moment, the reactions will develop a couple in the opposing direction. Since the moment is in the clockwise direction, the reaction couple in the supports will be in the counterclockwise direction. Let's go ahead and solve them by taking sum of the moments about A equals 0. This will allow me to solve for B sub y. Moments positive in the counterclockwise direction. B sub y times the length of the beam forms a positive moment. The concentrated moment m naught, according to that sign convention, is in the negative direction. Set that equal to 0, and we get B sub y equals m naught over L. I'll write that in right here. That tells me that A sub y is equal to m naught over L, but acting in the opposite or downward direction. So there's my couple that resists the concentrated moment. Now for the shear force diagram. Our rule tells us that we have a reaction, a force pointing downward, m naught over L, so the shear force diagram will jump down by m naught over L. Then there's no distributed load over the beam, so the shear force diagram is going to be constant all the way to the end, all the way to support B. And then the shear force diagram jumps up by the reaction, which is equal to m naught over L, and comes back to 0. And of course this is a good check that everything went right. For the bending moment diagram, we have a concentrated moment m naught at the end of the beam acting in the clockwise direction. The rule tells us that our bending moment diagram jumps up by an amount m naught. Because the shear force is constant, the bending moment diagram will be linear. Because the shear force is negative, the bending moment diagram will be decreasing. And finally, we know that the moment must go to 0 at the right end of the beam because it's a pin support and there's no moment acting at the end. So I'll draw the straight line. That's supposed to be a straight line going downward. But let's do a quick check that the moment did in fact come back to 0. We start with m naught minus the slope, m naught over L times the length of the beam. Those two cancel out, and that does indeed come back to 0. Considering a slight variation on this problem, where the moment is acting somewhere in the middle of the beam rather than at the end, a quick calculation would tell us that that moment doesn't matter where it's acting, is still resisted by a couple in the reactions acting in the opposite direction, m naught over L. And in fact, the shear force diagram doesn't change, still jumps down by an amount m naught over L, is constant over the length of the beam, and comes back up at the opposite end, so m naught over L. The moment diagram, however, looks a little bit different. There's no moment at the end, so it starts out 0. Because the shear is negative, moment is decreasing. And the value at A is simply equal to m naught over L times A. This is negative, but I like to just draw the magnitude of, sketch the magnitude of the moments for consistency. Now we reach the concentrated moment in the middle, and the beam moment diagram jumps up by an amount m naught, which will make our moment in the middle equal to m naught times 1 minus A over L. Simply this value, which is negative, plus m naught. And then the moment diagram continues to decrease linearly and comes back to 0 at the end, which we could check fairly easily.